Hello everyone, welcome to Chemazon-Complete Chemistry. So in this video we are going to see all about the first order kinetics. We will derive the integrated rate expression and we will also draw some of the graphs. This is one of the graph of the first order kinetics. This is a rate equation and this is the final expression that we will get. Okay, so what is the rate equation for rate equation? Rate is equal to K is the rate constant into concentration of reactant. Let's say A gives product. This is the general reaction. Okay, and order is 1. Okay, so what is rate? Rate I can write as, we are writing it for reactant, so it will be minus change in concentration of reactant with respect to time is equal to rate constant into concentration of reactant. What I can do is I will rearrange slightly. 1 by A into dt dA is equal to negative sign I can bring on the right minus K. This dt I am bringing here. Okay, K dt. Okay, so we have got this expression. Now what we have to do? We have to do integration. Now if you remember, derivative of ln x is what? 1 by x. Derivative means breaking one particular expression. Okay, like for example, I break entire one big sphere into small spheres. This is called as derivative. Okay, if I do reverse, that I'm joining all these small spheres, that is I'm doing integration. Okay, I'm doing integration, then I will get the big sphere back. So if I do the integration of 1 by x, I will get ln x. So 1 by x integration is ln x. Okay, so I have to integrate here. Initial concentration is, let's say, A0 and final concentration is AT. Similarly, here also initial time is 0, final time is T. Okay, 1 by x dx, that will be what? Integration of 1 by x is ln x. So ln A, limits are initial A0, final AT. Similarly, here minus K is constant. Integration of dt. Okay, dt means small fragments of t. So we integrate dt, what we will get? We will get entire or complete t. Again the limits, t is equal to 0, t is equal to t. Okay, I'll erase this. Now what we have to do? We have to substitute the limits. How do you substitute the limit? Higher limit minus lower limit. So first we will write the higher limit. So higher limit here is 80. Okay, so we will write ln of 80 minus ln of initial concentration is 0, lower limit is A0. Okay, minus K into higher limit is T minus lower limit is 0. So T minus 0 is T. So this is minus KT. This is ln of 80 minus ln of A0. Now I don't want this negative sign here, so I can bring it on the left. So minus ln, okay, I will put the brackets, minus ln A0, which is equal to plus KT. Okay, so minus sign I will substitute inside. This will become minus ln 80, minus into minus will become plus ln A0, which is equal to KT. This I can rearrange. Minus, okay, this I can write ln A0 minus ln AT. What is AT? It is concentration of the reactant after time t. Okay, now if you remember this log expression, ln of A by B is ln A minus ln B. Okay, so ln, this is A, this is B. So I will write ln of A0 by AT is equal to KT. Now ln is present, so here the base is E. Okay, so from this is the final expression. Ln A0 by AT is equal to KT. A0 is the initial concentration of the reactant. A0 AT is the concentration remaining after time t. K is the rate constant, T is time. So now we can plot some of the graphs. First is I can plot ln of A0 by AT versus time. Okay, so we have seen the relation just now. ln of a naught divided by ln of at is equal to e raised to plus kt. Okay, sorry, is equal to what? Is equal to kt. So we are plotting this. So this is my y, this will be on my y-axis. This is slope. This is x plus 0. So y-intercept is 0. C is 0. So it will be a straight line graph. Okay, ln of a naught divided by at, and here we have time. So this is plus, so it will be a positive slope. Is there any intercept? No. So it will pass from the origin. Line will pass from the origin. Slope is k. This was a first graph. A second graph what I want to plot is a naught by at versus t. This is the second graph. Third graph is at by a naught versus time t. Now a naught by at, if I want to rearrange this equation, okay, ln of a naught by at, base is e, this is kt. So a naught by at will be what? You take the power, right? E raised to kt, e raised to plus kt, right? So this will be what? Here the graph will be, I'm plotting a naught by at versus time t. Okay, I'm plotting time t. So this is what? Exponential function. Plus means it will be increasing. Okay, so it will be like this, exponentially increasing curve. This is called as exponentially increasing curve. Increasing curve. Okay, now here if you see, okay, here if you see, initially what was the equation? Okay, let me write the equation again. Ln of a naught by at is equal to e raised to plus kt, right? Now what will happen? I will take the reciprocal of this. When we take reciprocal of this, at by a naught, this will become e raised to minus kt. Okay, a naught by at is e raised to plus kt. If I take the reciprocal, this will become e raised to minus kt. That is, or I can write like this, I'm taking reciprocal, so this is e raised to plus kt. It will go to the numerator, plus will become minus, e raised to minus kt, like this. So now it has become what? Exponentially decreasing curve. So again I'm plotting, now I'm plotting at by a naught versus time t. So what I will get? I will get a exponentially decreasing curve like this. Like this. This is what? This is called as exponentially decreasing curve. Okay, now one more graph we have to see. The plot of ln of at, ln of at versus time t. Now we had seen the equation ln of a naught minus ln of at is equal to kt. So we want this on the y-axis. So this I will bring here, kt will come on the left. So what I will get? Ln of a naught minus kt, which is equal to ln of at. So this I can rearrange. Okay, just this I'm writing here on the left, which is equal to minus kt plus ln of a naught. Now this is again of the form slope intercept form. This is y, minus k is the slope m. This we will plot on the y-axis. This is the, sorry, this will plot on the x-axis. Y is equal to mx plus c. C is the y-intercept. So how will the graph look like? Ln of at. On the y-axis we have time t. Sorry, on the x-axis we have time t. And then now negative k. Minus k means it is a exponentially, it is a straight line with a negative curve like this. What is the slope? Slope is minus k. And what is a y-intercept? Y-intercept is what? that is this value. This value is what? This value is given ln of a naught. Okay, that is C. C or y intercept is ln of a naught. Now we have to see one more graph. Okay, fifth one. We had seen we have seen the rate, right? Rate is equal to K into concentration of the reactant at time t. Okay, so what we have to do, we have to plot the graph of rate versus concentration of the reactant. Rate rate versus concentration of the reactant. Now if you see, this is of the form y is equal to mx plus c is what? 0 plus c slope, y-intercept is 0. So this will again be straight line. Slope is what? Slope is rate constant k. Okay, so this was the fifth one. Now what I have to do is, okay, I have to plot, I think this many graph is enough for now. So we have total plotted how many graphs? 1 2 3 4 and 5. Okay, so always remember, now we have written in terms of ln. What will happen when I write it log? How do you convert ln to log? Suppose I write value of ln2. I want to convert it into log2. How will I convert it into log2? Multiply it by 2.303. Okay, multiply whatever value is given, you multiply it by 2.303 and ln will become log. Okay, so you will get to see the term 2.303. So it's very important to check whether they have asked ln or log. Okay, I hope you have understood how to derive the expression and all the graphs. Thank you.